So what does a confidence interval mean? Well, if we think back to sampling distributions, see, I told you sampling distributions are key. So here's a curve. Here's a sampling distribution for x bar. It says, and what we have here is we have a whole bunch of samples, and what we did is so here's the point estimate for this first sample, a little bit less than the population mean mu, and here's the confidence interval, here's the lower bound, and here's the upper bound. So we captured, even though, I mean, here we know what the population mean is. See how this confidence, how this one sample and the associated 95% confidence interval did indeed have the true mean in it. And the same thing here. I mean, the point estimate was high, this X bar was high, but the confidence interval actually captured it, and so on and so forth. Then you see how this says this one missed it. So why is it a 95% confidence interval? I'm counting. Does it tell us how many samples there are? I guess we are stuck counting them, huh? So, what does that say? Let's a minute here. Maybe I can read what it says. So there's 25 samples here, and 24 of them caught the true mean, right? You see, just that one missed it. So what is that as a percentage? 24 out of 25. Well, let's see. That times 4 and that times 4 makes it out of 100. What's that? 96. So this is a 96% confidence interval actually, because you know 24 out of 25 caught the true mean. So there was a 4% chance that it didn't catch it. Okay, and that's what. Well, I mean, they're saying 95, and it's just because of the number of samples. But if we had 100 samples and we had a 95% confidence interval for each of those samples, that tells me that 95 95 of the samples we would capture the true mean, and 5 of them wouldn't. And that's what, if we had an 80% confidence interval, 80 out of 100 samples would catch the true mean, and 20 of them wouldn't. 99% confidence interval, 99 of the 100 samples would catch the true mean, one wouldn't. Okay, so that's all a confidence interval is. Um, and that's what it does. And so when we actually come to creating a confidence interval, okay, so this is the one problem we probably should have worked, 'cause I'm not sure what you folks look at out of the textbook. I think some of you do. I think some other you would benefit from looking at some of these exercises. So here's a problem we're talking about changing the margin of error. Now, what you got to remember, and I'll do this from a mean point of view, but the same thing is true for a proportion point of view. So when we calculate a confidence interval, we take this point estimate, the sample mean, plus or minus some z-score, then that depends on the level of confidence. And of course, then you probably have read or watched about the t-score too. It's the same kind of idea. And then to get the standard deviation, we'll take the population standard deviation divided by the square root of n. If we get the population standard deviation, and we've got a big enough sample size, we're going to use z-scores, right? So if I have a okay, so and this is the margin of error part, right? This is what you add or subtract to the point estimate, to the mean, the E, as they said right here. So what happens if we increase the level of confidence? What happened to the margin of error? So if I'm at a 90% confidence interval, if you look at that little mini shortcut table, just a minute, let me get a picture of that. So this is from the bottom of the normal curve table in Dr. Stevens' book. It's a really nice thing. Other textbooks don't do this, and so it's a really nice feature to have. Now this only works for z-scores, which if you know the population standard deviation, you get a big enough sample, or if you're dealing with proportions, that binomial approximation. This works. So if I'm looking for a 90% confidence interval, the z-score that I want to use, now this is what, remember that, here, let me write this down, 1.645 plus, times that standard deviation divided by this by the square root of the sample size. Remember, this is that standard deviation for the sampling distribution, and this is what we add or subtract. And let's see, where was I going with this? Um, so um, this would be what decides. You have your point estimate, and then how far down you go. Okay, and versus a 95% confidence interval. Well, that makes the z-score 1.96. You see how this is a bigger number? So this is how many standard deviations. So here's the standard deviation. This is how many standard deviations you're going to go above and below the mean. I mean, if we were back using this empirical rule, the 90, 68, 95, 9.7 rule, we'd be using 2. And that works, but it's not as exact as we need to make it. And all the software doesn't use 2. And then notice what happens with the 99% confidence interval. You're going to go 2.575 standard deviations either side of the mean. So what happens when you increase the level of confidence? The margin of error gets bigger because you have to encompass those bigger, higher levels of confidence to make sure that you catch that unknown population mean. See, now, unlike that picture I just showed you in this video where we knew the mean and we were looking at the confidence intervals, now we don't know the mean, but we know the way confidence intervals behave. And so now at these levels of confidence, that's the percent confident that we're going to actually catch the population mean. And like if it's a 90% confidence level, with a 10% chance, or 10 times out of 100, we will fail to catch the population mean. It'll be a bad estimate. And 5% of the time, and 1% of the time, we'll fail to catch the population mean in our estimate. Okay, and we don't know if we're right or wrong, but we don't know if we did catch it or not, but we know by the confidence level, we know the likelihood of us not getting it. Let's see if I can move this out of the way. If you decrease the confidence interval, what happens? Well, you do a lower z-score, so that would tell us that the margin of error decreases because you don't need to have to go out to many standard deviations. What happens if the sample size increases? So let me ask you this. This is a new thing. So what happens when the sample size increases? So let's say we're going to do a 95% confidence interval. So z star is 1.96. And I don't know, let's make this up. Suppose we got a population standard deviation of 15, and and this comes from a normal distribution. So I'm going to go with a sample size of 10. That's going to be maybe I should go with numbers that are easy to do instead of square root of 10. Suppose I got a sample size of 16. So that means I'm going to do 15 divided by 4, which is what? 3.75? I'm guessing. Something like that. So then we got to go 1.96 times 3.75, okay? That's that level. What if we increase it to say 49? We can take the square root of 49. It just won't be so easy to calculate it here. Can I erase this? Yes. So if I go with the square root of 49, I have a sample size of 49. Well, then I'm going to take 15 divided by 7.5. What is that? 2.227, right? Yeah, 2 1/7. So 2. I think it's 1.4. Blah 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 blah. Okay, so before with a sample size of 16, it was what, 2.75, and with a sample size of 49, the standard deviation is smaller, which means 1.96 times that smaller standard deviation isn't as wide as an interval. What if we go up to something huge like a 4,900 sample, right? Well, that would be 70. 15 divided by 70 is a less than 1, way less than 1, less than a half. So that means it would be a really tight, very very narrow level of confidence. So increasing the sample size is one way to bring down your margin of errors. Decreasing your level of confidence is one way to bring down your margin of errors. What happens is collecting large samples is expensive, so research companies will usually do some kind of maximization. There's all kinds of formulas for that, which we won't go into. Okay, so I hope I answered your question about what what is a level of confidence and what does it do? Okay, it just helps ensure that you're going to have a good estimate that your low and your low to upper will capture that true population parameter, which we don't know, and that's what we're trying to estimate.